We already looked at how to evaluate limits analytically, which would be as the limit of the function f of x as x approaches c is equal to r. Now, there's two other common methods, or two other common representations of limits. And the first one I want to go over is that of representing them graphically. So, if we were to do you want to evaluate the limit of, let me sketch a graph of f of x, or f of x is equal to x squared. So, let me 6, 1, 2, 3, 4. Then I go to here 1, 2, 3, 4. And then my y is equal to x squared. So sketching it, I will do something like this. Should we know how to sketch x squared by now? There we go. So what I want to do is figure out the limit of x squared as x approaches 1. So what does that mean in terms of the graph of x squared? Well, that means, remember from the definition, that you want to get arbitrarily, like, the value you want to approach, your x approaching, you want to arbitrarily approach your x values to 1, but not equal to 1. So, if you were to just get arbitrarily close to x is equal to 1, you would want to look sort of as if you were to follow like that. You would see, well, going from this direction, because you're trying to see what values it approaches no matter what direction. So you can look from that side as well. So you would see, okay, well, what value does f of x is equal to x squared seems to approach as your x values get arbitrarily closer and closer to 1. Well, it seems that the f of x values are getting closer and closer to 1, because here you might have gone 0.5, here 0.75, here 0.9, 0.99, 0.99, and then the same thing over here, 1.5, 1.25, 1.1, 1.01, 1.001, and it seems that you're getting closer and closer to x is equal to 1, just based off of this graph. So you would say that the limit of f of x as x approaches 1 is equal to 1. Also, as you would just give the function definition, it will. Oh, come on. Oh, what's going on? Why does this always happen whenever. When I'm doing stuff on my own, this never happens. So when I'm in a meeting or if I'm recording something, it never wants to cooperate. I don't know what's wrong with this. There we go. So the limit of f of x, sometimes you do just define the function right there. So the limit of f of x is equal to x squared as x approaches 1 is equal to 1. So this is how you would write it out. This is how you would represent the limit in, I guess, words. So you could do that graphically like that. Or we could, another common method of representing limits is numerically, which essentially just refers to a table of values. X and f of x. So we could try, we want in a table of values, just like in the graph, we want to take values of x that are getting arbitrarily closer and closer to x is equal to 1, but not equal to x is equal to 1. So we could take 0.9, 0.99, and then 0.999, and then we could do 1.001, and to extend this table, 1.01, and then 1.1. speaking to that, but I think we're fine. Just like that. Now, I'm just gonna bring out a calculator and see what each of these evaluate to. So, let's pull this out. So, x squared. So this, first of all, is 0.9 squared. What is that? So this is gonna give me 0.81. Now, what if we did 0.99 squared? That's 0.9801. If we did 0.999 squared, that would give us 0.998001. Alright. Now, if we did it from these values that are greater than 1, we could first do, let's start from the furthermost one, 1.1 squared. That's 1.21. Then if we do 1.01 squared, that's 1.0201. Now if we did 1.001, that would be 1.002001. So if we were given this table of values, what would we estimate the limit of f of x as x approaches 1 would be? Well, you would follow it from, again, just like here, you follow it from both directions. For values less than 1 that are getting closer to 1, and values greater than 1 that are getting close to 1. We would see that as these values get closer and closer to x equal to 1, our f of x values are getting closer and closer to f of x is equal to 1. So we would estimate that the limit of f of x is equal to x squared as x approaches 1 is equal to 1. I don't want to write the whole thing out again. So it's the same statement. So this will be our estimation. So we can't 100% conclude that is the value that it is approaching. We would need to uh, do maybe be a little bit more rigorous, because right now just estimating from a table or a graph isn't fully enough to determine the exact limit, but it does give us a good estimation of the limit. So graphically really just refers to a graph, and numerically really just refers to a table of values. Now something interesting I want to point out as well is, what if we try to maneuver this function somehow? So get rid of that. What if, oh no, okay, I guess I'll just do black because I don't want to do the whole thing. What if this point over here was undefined? Draw my circle then. So if the point over there is undefined at x is equal to 1, so maybe we've defined our f of x to be equal to x squared when x is not equal to 0, and let's say undefined, like that, when x is equal to 0. Or I guess another way you could write it is, you just, instead of a piecewise function, you could just say f of x is equal to x squared for x is not equal to 0. I guess that would be the better one to choose. So here, how would you estimate the limit of f of x equal to x squared to be as x approaches 1? Well, for the values that are less than 1 that are approaching 1, it still seems like the f of x values are getting closer and closer and closer to 1. Same thing for the right side. With values that are greater than 1, if you keep getting closer and closer to x is equal to 1, your f of x values are getting closer and closer to f of x is equal to 1. So, again, you would say that the limit of f of x is equal to x as x approaches 1 is equal to 1. Now, what if we had a point that was defined up there, and then maybe we can use a piecewise function to say that f of x is equal to x squared for x not equal to 0, and 2 when x is equal to 0. So, again, we can look over here and say, actually we could do it numerically for this one not even defined there. And again, it would just be, whoops, well, I don't know what this one was from. Oh, it's from this one, alright. So, if you're looking at a table of values, you would say, okay, well, 1 isn't, f of x isn't defined at x is equal to 1, Well, it doesn't really matter because it's not like we're defining f of one. We're not talking about a one in the rows over here. We could include a one over here and say it's undefined, but with the limit, we don't really care about x getting arbitrarily close to one, but not equal to one. So even a table of values, you don't need to define what f of one is. So this is just enough as well. So going back to our uh, this one here, f of x equals to x where x not equal to 0, 2 x is equal to 0. The limit, again, same idea, for values less than 1, if you keep getting closer and closer, no matter which direction you're approaching 1 from, you seem like you're always getting closer and closer to 1. So again, even if this was your new function, you would say this statement over here, the limit of f of x is equal to x, so x approaches 1 is equal to 1. And again, with the table of values, you don't care about the value x is equal to 1, so you don't even include it. So you would just look at values that are less and greater than 1. They're getting closer and closer to 1 and seeing what these values are getting closer and closer to. Now, one last exercise I want to go over is actually knowing how to set some of these notations. So, if I had the limit of x cubed is equal to 0, this, well actually I kind of said it out loud, this would be the limit of x cubed as x approaches 0. And if we had something like the limit of, let's say, 4, limit, or I'll say like this, LIM for x 5 and 6, x arrow negative 7, what that translate to. So that would be said out loud as the limit of 4x to the 5th 6 as, and then we're saying, actually instead of vector, they use another variable. Let's use w. So remember, this is a function of w, so it doesn't make sense to take any other variable. It has to be w approaching negative 7. So the limit of 4w fifths, or 4w to the 5th 6 as w, and so now we're gonna write this w approaching negative 7. So w approaches negative 7. Alright, so I'm gonna give some of the limits. So you have the limit. Oh, actually, I'm trying to say LIM. Actually, I'm gonna write it out without even saying anything. Do, 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 uh, do. So, what do you think this would translate into if you would say it out loud? So, we will begin with, well, LIM, that's just a notation for a limit of, and we would take the limit of whatever we have over here. So this doesn't really actually have a name unlike other things, like if you're familiar with the radicand, and there's something else that we also have like a name of, something like this. But when you're talking about limits, you don't actually have a name for this, or if there is, I don't know it. But we would say the limit of this function right here. Well, I guess whatever comes right after the LIM, the limit of the 7th root of 8b to the 9th, and then after you write the limit of whatever this thing is, you would say this thing over here, which translates to as v approaches 10. As v approaches 10. Alright, maybe we can try another one. We had I'm not gonna say things out loud. Alright, so again, what do you think this would translate to out if you would say it out loud? Alright, so again, we're talking about LIM, which is how we would shorten limits. So that LIM means we're taking the limits of something, limit of what? Well, it'll be the thing that comes right after the LIM. This business over here. The limit of 10 absolute values of negative u to negative 2, and then once you write the function you're taking the limit of whatever function, you would then say the whatever the value u is approaching. So as the thing that's below the LIM, u arrow negative 3, as u approaches negative 3. So if you were to see these limits here, this is how you would interpret them. If you were to have this notation, for example, if you had this, you would interpret it as the limit of x cubed as x approaches 0. And if we knew that this value was equal to, I don't know, 9, then you would say the limit of x cubed as x approaches 0 is equal to 9. Or if you just had this standalone expression, then you would just say it out loud like this.